Welcome back, everyone. Today, we're taking a massive leap out into our solar system to look at its biggest and, honestly, most mysterious neighbor, Jupiter. I absolutely love unpacking cosmic mysteries, and today we've got a fascinating new explainer for you. For a long time, we thought we had Jupiter totally figured out, at least on the inside. But as is usually the case with science, the universe just loves to throw us a curveball. We're going to dive into a brand new, falsifiable scientific hypothesis that attempts to finally solve a puzzle that's had planetary scientists scratching their heads for the last few years. It all really starts with this simple question: what is actually hiding inside Jupiter? Now, to figure that out, NASA sent the Juno spacecraft all the way out there to measure its gravity. Since we obviously can't physically drill into a gas giant, measuring gravity is really the best way to see how all that mass inside the planet is distributed. When Juno beamed that data back to Earth, scientists were expecting a pretty standard reading, but instead, they got a totally unexpected answer. This data completely challenged decades of textbook planetary science. Okay, let's dive into this old belief versus the new discovery. We used to think that Jupiter had this sharply bounded, really compact solid rock core. Basically, imagine a hard, dense ball of heavy metals and rocks right at the dead center, just surrounded by thick layers of gas. But Juno's gravity measurements, they proved that Jupiter actually has a dilute or fuzzy core. So instead of a hard, solid ball, the heavy elements are spread way out across this massive giant region deep inside the planet, just blending smoothly right into the hydrogen and helium gas. Now, knowing that this fuzzy core exists is one thing, right? But figuring out exactly how it got there is a totally different problem. The scientific community has been trying to use standard theories to explain it. Some folks thought, well, maybe the rocks just slowly dissolved over time into the gas. Others proposed that a giant impact, like imagine another massive planet just smashing right into Jupiter, broke apart that solid core. But here's the catch. Recent high-resolution supercomputer simulations show that those ideas just do not work. They fail to explain how this giant fuzzy structure was created in the first place, and more importantly, how it actually survived without completely mixing away over billions of years. Section 1, the ADWE hypothesis, a novel solution. Now, what's really interesting about this next part is that because those standard theories fall so short, we desperately need a fresh perspective. We need a process happening during Jupiter's violent formation that could spread out these heavy elements without completely mixing up the whole planet, and then, this is absolutely crucial, shut off so the structure survives to the present day. That brings us to a novel, highly detailed scientific framework authored by Kevin L. Brown. He's a researcher, inventor, and author. He recently published a paper outlining a falsifiable hypothesis. And by falsifiable, I mean it's strictly designed to be rigorously tested and either proven right or proven wrong by the scientific community. It's just an incredibly clear and structured piece of planetary physics. Brown calls this hypothesis ADW, which stands for Accretion-Driven Wave Entrainment. Now, I know that sounds like a mouthful of big academic words, but let's break it down to an 8th grade level. Accretion literally just means rapidly gathering gas. Picture early Jupiter pulling in massive amounts of gas from space. As all of this gas slammed into the young planet, it released a huge amount of energy, creating massive pressure waves and violent turbulence deep, deep inside. Basically, ADWE proposes that this violent process acted like a giant mechanical blender. Imagine a massive swirling storm stirring up sand at the bottom of the ocean, pulling those heavy elements outward and making the core all fuzzy. Section 2, the mechanical mixer, Triune harmonic dynamics. To really understand exactly how this giant planetary blender works over time, the hypothesis breaks the formation down chronologically. Let's look at this mechanical mixer in action through 3 really clear steps. First up, we have the base phase. This is just where ordinary planet formation processes build up an initial, highly concentrated core of heavy elements. Next comes the pressure phase, and this is the chaotic part. Jupiter starts rapidly swallowing huge amounts of gas in a runaway effect that injects massive mechanical energy into the planet, causing that violent turbulent mixing we just talked about, which spreads the heavy elements outward. Finally, we hit the integration phase. The gas supply runs out, the accretion weakens, and the giant blender naturally just turns off. The swirling settles down, and the newly formed, wider, fuzzy core stabilizes. So the crucial point is this specific number, 4.56 billion. Because that violent gas swelling phase was strictly temporary, the mechanical blender eventually shut off entirely. Think about it. When the power gets cut to a blender, the spinning stops.
And because it stopped, the expanded, fuzzy core became locked in place. It essentially became a stable, frozen fossil deep inside Jupiter that has successfully survived for 4.56 billion years, right up until the Juno spacecraft flew by to measure it.
Section 3. Validating the theory. The experimental protocol.
You know, a great idea simply isn't enough on its own. You've got to prove it. A robust hypothesis has to be rigorously tested. So Kevin L. Brown laid out a strict, step-by-step experimental protocol for scientists to run in advanced supercomputer simulations. The simulation starts with stages A and B, establishing a basic young planet and then triggering that massive runaway gas storm. Then in stages C and D, the computers must actively measure if enough wave energy actually reaches the deep core to mix the heavy elements. Stage E shuts the gas storm right off. Stage F fast-forwards the planet 4.56 billion years into the future. But the absolute most important part is Stage G. The final computer model must be blindly compared to present-day Jupiter without any artificial tweaking whatsoever. If the computer's output matches Juno's real-world gravity data naturally, then the theory is validated.
Section 4. Falsification parameters. How to prove it wrong. The mark of a good hypothesis is that it gives you the exact blueprint on how to destroy it. And this brilliantly illustrates what makes for truly objective science, falsifiability. Kevin L. Brown specifically designed ADWE with really strict failure parameters. The hypothesis is instantly proven wrong if the simulation shows that the deep wave energy is too weak. It fails if the turbulence stays too close to the surface and doesn't ever reach the core. It fails if the heavy elements just refuse to mix outward. It also fails if the blender is actually too strong and completely homogenizes or mixes up the entire planet perfectly evenly. And finally, it fails if the fuzzy core is created but somehow gets destroyed before that 4.56 billion years passes. If even one of these happens in the supercomputer, ADWE is completely out. Now that is incredibly rigorous science. Just to wrap up the technical mechanics here, I want to read part of the final one-sentence hypothesis straight from Kevin L. Brown's paper. Quote, Jupiter's extended dilute core formed when pressure waves, shear, and turbulence generated during runaway gas accretion transmitted sufficient mechanical energy to entrain material outward. That one sentence just beautifully condenses that entire giant blender concept we've been unpacking today.
Section 5. Real-world implications beyond Jupiter.
Let's move to how this builds into our understanding of the broader universe. Because honestly, if this hypothesis passes those strict supercomputer tests, it doesn't just change how we look at Jupiter. It completely changes how we look at planetary formation as a whole. See, right now, we mostly look at Jupiter's core as a static record of what it ate, just a list of the heavy elements and rock ingredients that fell into it. But if ADNWE is correct, that dilute core becomes a dynamic, living fossil record of how Jupiter created them. The fuzziness of the core literally records the violence, the speed, and the sheer power of the gas storm that birthed the planet.
Which leaves us with this really incredible thought to ponder. If Jupiter's fuzzy core is actually a fossil record of its violent birth, what does that mean for the billions of giant exoplanets scattered all across our galaxy? Every single gas giant out there might have a completely unique interior architecture based entirely on how violently it gathered its gas. Two planets with the exact same ingredients could look totally different on the inside just because of how their mechanical blenders operated. It really makes you wonder what kind of spectacular, turbulent storms are frozen in time inside the cores of planets we haven't even discovered yet. Thank you so much for joining me for this explainer. Keep your curiosity sharp, and I'll catch you next time.